Okay, so pick a fixed equilateral triangle. Here's its circumcircle, and pick a point P on the circumcircle and draw a tangent. This red parabola is the isogonal image of this tangent with respect to this equilateral triangle. So as I rotate P on the circumcircle, I get a different circumparabola, correct? Now, because everything is so tight here, let's go ahead and look at these very singular associated objects. For example, the locus of the focus of this family of circumparabolas. What are these curves? I don't know. If anybody can take a guess, I'd be more than appreciative about it. But there are these three green curves. They're actually the same curve, but there are three branches of them. What is the degree of this curve? Any geometric interpretation about it. So that's the first observation. Very interesting locus of the focus. Over complete revolution of tangents through P, the focus is gonna move into this branch and it's gonna come back through this other branch and then escape and escape and escape. So it has a very nice, if you consider the extended plane, it has an interesting topology. Is it a knotted topology? Is it a self-intersecting topology? What is it? Okay, so this is the first thing. The second thing we can look at is what is the envelope of the directrix. Let's go ahead and scale this out. And I'm going to try to recenter this guy in the middle here. And what am I looking at right now? I'm actually drawing the directrix. I hope I did this right. The directrix envelope. Yeah, well, I should be extending this directrix further out, and it would actually be tangent to its magenta envelope. But if I actually jog point P around a little bit, I'm hoping that if this thing doesn't bump, there you go. Let's go ahead and scale this up a bit. You can see here that this is in fact these three branches of a magenta curve that connect up at infinity are indeed the envelope of the family of directrices associated with this family of circumparabolas, right? So if I can go back to drawing the focus locus, we saw that before, and I'm now drawing the envelope of the directrix as, again, my equilateral triangle is fixed, and all I'm doing is I'm actually jogging point P along the circumcircle, and I'm watching this family of directrices, and I'm drawing here the envelope of these lines. Okay. Okay, so now I actually want to show you guys a couple of phenomena associated with the polar triangle to this fixed equilateral, but with respect to a moving circumparabola. So the polar triangle is going to be a family. So as I vary P over here and I choose a different tangent, I'm going to get a different polar triangle, right? You can see these polar triangles as expected. Their circumcenter passes through the focus of the reference parabola. So this parabola here can be thought of as being inscribed to the orange polygon, and conversely, you can think of the orange polygon as being the polar of the blue equilateral with respect to this parabola, meaning its sides are tangent to the parabola at the points of contact here. Okay. Now, when you do this, you notice right off the bat a very interesting phenomenon, which is probably obvious, but I don't recall having seen this described anywhere. The circumcenter, so we just saw that the circumcircle of the polar contains the focus of my circumparabola, but we just noticed here that there's a collinearity between the choice of my tangency point on the circumcircle, the centroid of my fixed equilateral, and the circumcenter of my polar. Let's go ahead and change P. I'm going to go ahead and jog P along the circumcircle, and you're going to see that this collinearity is maintained, and that's quite curious. I'm sure there's a straightforward proof via perhaps barycentrics or trilinear coordinates that can show this phenomenon, but I wasn't aware of that. This is phenomenon number one. Phenomenon number two, let me look at my script here, is the fact that, okay, so what I can play with now is I can play with loci of triangle centers of my polar family. So let's go ahead and draw the locus of x1. So here's the locus of x1, and what do I mean by this? As I jog P and I get a different circumparabola, I get a different polar triangle, and I can compute x1, it's in center, it's going to be in the interior of my polar triangle, and I can look at what kind of curve the family of polars is going to trace. There you go. Given a particular choice of P. So it's these three branches, these three magenta branches. They don't look particularly interesting. Let's go ahead and now look at x2, slightly smoother. Let's see here, I actually have a script of which points are cool. Yes. Yes. Okay, so this is x2. How about the circumcenter? We saw that the circumcenter is collinear, circumcenter of the polar, with the centroid of the equilateral and point P, right? So if I change P, I get this collinearity. However, the circumcenter itself is not doing anything interesting. How about the orthocenter? Now the orthocenter traces this curve, and you visually are reminded of what we saw before, the directrix of the envelope of these parabolas. So let's go ahead and turn off x4 locus, and I'm going to light up the envelope of the directrix. We know that the orthocenter of the polar is going to be on the directrix, but what becomes apparent is that its locus is the envelope of the directrix. So now I'm lighting up both of them, they're just superposed. I'm going to turn off the directrix envelope, and you're going to see that they're exactly the same thing. So this is a very first curious observation here, or second perhaps, is the fact that the locus of x4 of the polars seems to be precisely the envelope of the directrices, meaning that x4 is marking the instantaneous center of rotation of my directrix family. So you can see the directrix is this red dashed line here, and it seems to be rotating precisely about the x4 of the polar for the specific case of the equilateral triangle. What else do I have here? Yeah, so x8, well, let's go ahead and go through the low number Kimberlin centers. You can see here this is the locus of the center of the Euler circle, 9-point circle. Here's the center, here's the locus of the cymedian, and the locus of the Jorgon point, and then you get to this nice locus of x8, which is the Nagel point. So the Nagel point, the locus of the Nagel point are three compact petals. How cool is that? So as I jog P around, x8 is going to be going through a petal. And then it's probably going to discontinuously jump from one petal as I go through infinity to another petal over here. Very cool. How about x9? Not that interesting. And then you got a bunch of you got a bunch of phenomena that one could study. And I'm going to go ahead and fast forward to say x15, because this guy here seems to have three cusps. And then I'm going to show you guys x20. x20 is basically a infinite channel kind of curve, right? They connect up at infinity. So again, interesting thing to study what this thing is about with the extended plane. We get the same phenomenon for the Bevan. So x20 is called the de Longchamp point. It's a reflection of the orthocenter on the circumcenter. Then x40 gets us a similar but distinct three-channel locus. x40 is the circumcenter of the excentral triangle. In this case, the excentrals of the polar, right? So if I jog the polar around, I would have to compute the excentral triangle, and I would notice that x40 is actually following this three-direction crossroads kind of locus. X55, I thought it was nice because it has like a, is it X55? It has a pointy locus. It almost looks straight line, right? These almost look like straight lines, but they cannot be straight lines. These are probably very flat, almost straight line curves. And then they go through this little transition here. I don't know if this is a regular point or if this is a cusp. Then you get into these interesting guys. X69 is a smooth locus, which is compact, so that's kind of surprising because the polars are not compact. And it's actually touching the regular polygon at its midpoints. And you get the same phenomenon with X76, but then you get these touch points at the midpoints, but then you get a little quite nice looking loop, right? At each one of the ends. And it looks like the touch point at the midpoint happens precisely when the parabola goes through infinity. So you're going to see that. You see right there, parabola is going through infinity, and X76 is approaching the midpoint of a particular side. So that's quite interesting. But it stays finite, it stays bounded. Okay, we got the same phenomenon with X95, and got this kind of star shaped locus, also undergoing the same phenomenon. It touches the sides of the equilateral when the parabola goes through infinity. And then finally, I'm going to show you guys X99, the Steiner point. The Steiner point produces this rather beautiful trefoil clover. And if you light up the locus of the focus, you notice that the latter is tangent to the leaves of the clover in a very beautiful way. So X99 is actually undergoing these three, it's compact, right? It's undergoing these three loops, and it touches the equilateral from the interior, which is a phenomenon we had not seen before, at their midpoints. So quite nice. Recall that X99 lies on the circumcircle of the polar, so it's going to be on the circumcircle. Since the circumcircle contains a focus, here's a very interesting question. What is the choice for, let's put it at 20. Yes, let's put it at 25. Yeah, I had not thought of this. Is this going to be a trivial number? 40, 45. Yeah, okay, so 41, 42. It's before 41. It's maybe near 39, 38, 37. So look at what's happening here. Right here, approximate rotation of P with respect to horizontal by 37 degrees, and that's an approximate value. X99 mysteriously coincides with the focus of the circumparabola associated with that particular tangent. So what is that exact number? Is it, yeah, it's below 37, maybe 36.5, maybe a little more. Yeah, looks like it's pretty close to 36.8 degrees. So here's a conjecture. If P is at 36.8 degrees with respect to the horizontal, the X99 is going to coincide with the focus of the circumparabola, which is the isogonal image of that particular tangent. What is that number? Is that even algebraic? Okay, guys, having a lot of fun with parabolas and circumparabolas. I hope to see you in the next video. Bye.